All right, so we're going to talk about parametric equations. Parametric equations are a set of equations that express two quantities as explicit function of an independent variable known as a parameter. It actually can be two or more equations, but we're only dealing with two dimensions, so it's going to be two equations. They are the form x is going to be a function of t, f of t, and y is going to be a different function of t. Here they call it g of t. This parameterization gives us a curve C, okay, in terms of t. You can use this to model motion in 2 or 3 or even 1 dimension. And often the parameter is t because t is used because a lot of times the parameter represents time. That doesn't have to be the case. It could be an angle or something, whatever. All right, so we'll start off with a basic example of like how to graph them. So we'll start off with something simple. Suppose a person transports himself into the coordinate plane and begins at the origin walking along the y equals 1/2 x. So we sketch his little graph. So we know that this means he's starting at, if we put him at the origin, then he would go at 2, he'd be at 1, and at 4, he'd be at 2, and at 6, he'd be at 3, and at 8, he'd be at 4, and at 10, he'd be at 5. And if we were going backwards, at -2, he'd be at -1, at -4, -2, -6, -3, -8, -4, and -10, -5. So that's what his path would look like, roughly, something of that nature. At any point in time, how does his distance along the y-axis compare to his distance along the x-axis? Well, we can see here that for any particular point, let's pick a nice easy point maybe to talk about. Let's go to this point right here, which is 6, 3. So we can see that his distance along the x-axis is 6, and his distance along the y-axis is 3. So the y distance is half the x distance. Y is half the x, which is really what y equals 1/2 x means. If he is moving 3 miles per hour along the y-axis, how fast is he moving along the x-axis? So if they tell us his y is 3 miles per hour, his y velocity, then his x velocity would have to be 6 miles per hour because it's always half. So his x-axis would be 6 miles per hour. Okay. In terms of t, we could represent his position as 2t comma t. And we could represent this with a pair of equations. And we would call them x of t is equal to 2t, and y of t is equal to t. All right? And we could plug these into our calculator. So if you want to know how to plug it into your calculator, you're going to add a calculator page. And after you add a calculator page, so if we want to add these to our calculator, you're going to add a graphing page. So add a graphs page. And once you do that, then you're going to hit menu, and then it's called graph entry edit. It might also say graph type, depending on when you last updated your system. And you're going to go down to parametric mode. and once you do that, it will come up and ask you x sub 1 of t, y sub 1 of t, depending on if you've already got parametric equations in there. And that will allow you to put in these graphs. The next thing is name another ordered pair and set of parametric equations that would produce the same result. Presume the same set of equations. Well, that could simply be we could do x equals t and y equals 1/2 t, because that maintains the fact that y is half of the x. But you could also have done, as a different example, x equals 4t and y equals 2t. Again, what you see is the y is half the x, etc. And you can see that there's infinitely many answers. So the main point of that is that there may be multiple representations of a parametric equation. And if you're not sure, go ahead and plug these equations into your grapher, and you'll see that you get the same graph. All right. So here's a graph to plug into your grapher. First of all, make sure your calculator's you're in parametric mode. When you go to your grapher, you should also be in radian mode. We're going to change the window. This t part, this is at the bottom of your graph where you enter your graph. It will say, x sub 1 of t, because it doesn't quite look like this. X sub 1 of t, y sub 1 of t, and then it will have for t, and usually the default is 0 to 6.28, etc. So what you want to do is change this 6.28 to 10. So we're going to change that to a 10, and then we'll plug these equations into your calculator. So the equations that you're plugging into your calculator are 5 cosine of t plus sine of t plus 0.5 t. And for the y coordinate is 5 sine of t plus 2 cosine of t. And if you do that, you should get a graph that looks like something like that. This is as close as I can sketch it. Okay. The next question is, what happens if you change the window, the t window, make it bigger? What you end up getting is more spirals. So try that and see what you get, but you should get more spirals. Okay. What happens when you change the t-step? Change it to a 2 and observe the graph. What happens? The graph should get more boxy. So more boxy, not smooth. What I mean like that, it would be like a bad connected to dot thing. So it'll look like this, with all these sharp corners and stuff. Alright, so now we want to graph one just simply by plotting points. You could also do it in your calculator to check, but we're going to do it by plotting points here to begin with. So what you do is you make a t-chart, but now it has 3 columns in it. One for t, one for x, and one for y. And you plug in the various numbers. So the first one I'd plug in is -1. If I plug in -1 into the x, that will give me -2 for the x. And when I plug in -2 into the y, I get -80. Alright, so I've plugged in all the numbers. At 0, I got 0, 0, etc. So I'm going to plot all of them here. Because the y values are big, I'm going to let my y's be multiples of 10. So each of these are going to represent tens here. So the 1 is 10, the 2 is 20, the 3 is 30, etc. Alright, so if I plot those points, and it's a good thing to plot them in order, and that's why you want to put your t values in order. It makes it easier to see an important feature of these graphs. So but what I'm plotting are only the x and y's. So negative 280 would be somewhere right about, that would be right here, and then 0, 0 is here. 248, that's somewhere about here. 464, so 464, somewhere about in here. And then 80, that's somewhere about in here. Oh, I skipped 648. 648 would be right in here. All right. And what we can see is this curve did this, and because we went with it with increasing time, we can actually put these little arrows on, because that's what's called the orientation, the direction in which the curve is plotted as t increases. So as t increases, it's moving along this curve in this direction. So here's another one. So take a second and do it. So I've plotted the points, I've labeled the points, now I'm going to plot them, 1, -1, 0, 0. So I plotted all the points, and so when I connect that with a curve, it ends up looking something like this. And my orientation would have been this way. Okay. All right, this one, I want you to take and just plug into your calculator using the grapher. I will spend a little bit of time talking about how to graph in class, since I can't do it here on the education video. But when you plug this in, you're going to get a really complicated looking graph. And it looks really roughly like that. So, now, the important question I want to talk about this graph, first of all, the main thing is to see that these can become very complicated. We're only going to deal with ones that are relatively simple. The second thing I want to talk about is, if we look at this graph, this is a y versus x graph, is y here a function of x? And my hope is that you're all saying no. And the reason it's not is because it fails our good old friend, the vertical line test. But then we have the next question, is y a function of t? Now, we didn't graph y here is a function of t, but we did when we talked about graphing. And if you remember, and I'm not going to get into too much here, but this graph for y as a function of t, I'm going to do it up here, would look something like this. We would put on the y equals t line, that would be our sinusoidal axis, and then we'd have a max and a min, and this graph would look something like this. This is t versus y. And you can see that this would be a function. The answer is yes, it would pass the vertical line test. And then we could do is x a function of t. Now this throws people off because we're going to put x here on the vertical axis. Because now for parametric equations, our independent variable is t, and that's what goes on the horizontal axis. But if we did that, this graph would look very similar to the last one. It would have, it would have my sinusoidal axis, and then this is a sine graph, so it would start at the origin and then do something like this. But it also will pass the vertical line test. So it is a function. And the reason that's important is because a lot of the stuff that we do in math is dependent on things being functions. So we can take this awful graph that we had here and apply a lot of math to it if we write it as a parametric equation, because then a lot of our function stuff comes in for free. All right. The graphs below represent the motion of a particle, and the